only. A household refrigerator is maintained at a temperature of 2 degrees centigrade. Every time the door is opened, see here, a household refrigerator is maintained at a temperature of 2 degrees centigrade. Every time when the door is opened, warm material is placed inside, introducing an average of 420 kilojoules, but making only a small change in the temperature of the refrigerator. The door is open 20 times a day. Door is open 20 times a day. And the refrigerator operates at 15% of the ideal COP. The cost of the work is 250, that is 2 rupees 50 paise per kilowatt. What is the monthly bill for this refrigerator? The atmospheric air is at 30 degrees centigrade. The atmospheric air is at 30 degrees centigrade. So the household refrigerator, then draw the diagrammatic sketch. Draw the diagrammatic sketch. So the directions of this one, that is the Q1. Don't forget about the directions and the notations. So this is the work input, this is the refrigerator, and this is the source. So practicing this is very important. Then you can go to the solution. So now what it is given? COP of a refrigerator. That means the desired effect is this one. So it is Q2 by Q1 minus Q2. And what about the temperatures? So here T2 divided by T1 minus T2. So what is this one? Maintained at 2 degrees centigrade. That means 2 degrees centigrade means 273. That is 275 Kelvin. Right? And the atmosphere, this is 30 degrees centigrade. 30 plus 273. So it is 303 Kelvin. So T2 value, it is 275 Kelvin. All the values are in absolute Kelvin, right? So T1, that is 303 minus 275. You will get the COP as 9.8, no units, right? But what is that? And the refrigerator operates at 15% of the ideal COP. So this is nothing but the 15% of the ideal COP. That is, this is nothing but ideally operated. Ideally operated. But when you take the COP of a refrigerator in actual practice, that is actual, is equal to 15%, that is 0.15 times the COP of a refrigerator in the ideal condition, that is in ideal situation. In ideal situation. So that is equal to 0.15 into 9.8. You will get it as 9.8. You will get that value as 1.4732. 1.4732. Right? Now, a warm material is introduced inside, introducing an average heat of, that means here. So the heat is the leaking. So that is equal to Q2, right? So it is of 420 kilojoules. It is of 420 kilojoules. It is of 420. That means what here? Heat to be removed in a day. Heat to be removed in a day. Introduce an average of 420 kilojoules, but making only a small change in temperature of the refrigerator. The door is open 20 times a day. So into an average of 420 kilojoules, and this is for one time. And you are opening it for 20 times. 20 times. So what you will get that Q2? It is more or less around 8,400 kilojoules. 8,400 kilojoules. right? So what is this one here? This one is nothing but equal to W, sorry, that is the first one is the Q2 you will get. So this is Q2 divided by W. Q2 divided by W, right? Then what is COP actual? It is 1.4732. 1.4732. 1.4732. Right? So what is the work required here? Now the work required, what you are going to get it is the work required from this particular cases, you will get it as 5701.87 kilojoule per day. Kilojoule per day. Kilojoule per day. Right? Kilojoule per day. Then in kilowatt hours per day. So that is kilojoules per day. Right? So then work is nothing but equal to, that is in kilowatt hours. So 1.583 kilowatt hours per day. That is, this is kilojoules per day. But if you want to get that in kilowatt hour, right? So that is per day means 24 hours. Per day means that is equal to 24 hours, right? So try to look that particular case. So here kilowatt hour. So 24 hours. So 5704 divided by 24, you will get as kilowatt hour per day, right? So that is electric bill. So what is that electric bill? If you are going to be getting like this particular case, so it is nothing but equal to 1.583 into what is that particular charge? It is that particular charge is 0.32. What is that particular charge? It is the 1.532, 30 rupees. Sorry. The cost of the work is, what is the monthly bill for this refrigerator? So 2.5, 1.583 into 2.5, 2.5. What is the monthly bill? So monthly bill means this is maybe you can get it is, this is for per day, and you can work it out for the month. That is 1 month is equal to 30 days. 1 month is equal to 30 days, right? So if you could work it out, electric bill per month, then what you will get it is in terms of the rupees. So here it is 2.50 per kilowatt hour. Per kilowatt hour. That is you should not forget. So the finally that charge you are going to be getting per month charge is 15.20 rupees, right? So this is try to observe this particular answer. So the procedure is this one, and try to observe the, so what is per day, what is hour. So in 1 day you will get 24 hours. So 24 in 1 hour is equal to 3600. So that is 1 minute is equal to 60 seconds. 1 hour is equal to 60 into 60. So 3600. So that is how you try to work it out, and applying to this one. So the answer is 15.20 kilowatt rupees. So that is the energy bill. That is the energy bill. So You can make this as in realistic situations also. That is how the says that is what. So the household refrigerator door, you should not open it for continuously. You have to plan and try to reduce opening of the household refrigerator as minimum as possible. Otherwise, very frequently, if you are trying to opening the household refrigerator, then each time when you open the household refrigerator door, the outside atmosphere will is going to enter, so that that compressor has to discharge the entered air into the refrigerator and giving more work input. If the work input increases, then automatically the electricity bill is also going to increase. So this particular problem is connected to that side. So the next one is the an ice making plant introduces an ice making plant produces the ice at atmospheric pressure. Ice making plant produces ice at atmospheric pressure and at 0 degree centigrade. See here, the problem is connected to the ice making plant. Realistic situation produces ice at atmospheric pressure and at 0 degree centigrade from the water. The mean temperature of the cooling water circulating through the condenser of the refrigerating machine is 18 degrees centigrade. Evaluate the minimum electrical work in kilowatt hour required to produce 1 ton of ice. So the enthalpy or the latent heat of fusion of ice at atmospheric pressure is 333.5. This is the standard value. Latent heat of fusion of ice. Every student has to remember. That means here the latent heat of fusion is nothing but the amount of heat required to convert water at 0 degree centigrade into the ice at 0 degree centigrade. Need 333.5 kilojoule per kg. Standard, but here it is the value is mentioned, but some situation you should have to remember as 336 kilojoule per kg. So this is the amount of latent heat of fusion. Latent heat of fusion. See, latent heat of evaporation. So for the latent heat of evaporation, the amount of heat required to convert water at 100 degree centigrade into the steam or vapor at 100 degree centigrade, you need 2255 kilojoule per kg. Kilojoule per kg. So these things, the standard values student has to observe. So now coming to this particular problem, the COP. So in this particular cases, because the parameter is essential parameter is COP. So that is the ice making plant is mentioned. So the COP, that means the lower temperature it is. So always the COP of a ice making plant. So it is the low temperature divided by the high temperature minus low temperature. So that is 0 degree centigrade means it is 273 Kelvin divided by the 18 plus 273. So it is 291 minus 273. You will get it as a 15.2. 15.2. Then this is nothing but equal to Q divided by, that is heat divided by minimum work input is required. So that minimum work input, that is nothing but equal to 15.5. Right? So you need to calculate what is the minimum work input. That is equal to Q divided by 15.2. 15.2. So what is the Q value here? That is 1 ton of ice is mentioned. So 1 ton of ice means 1000 kg. 1 ton of ice means 1000 kg into the latent heat of fusion of ice. That is 333.5 kilojoule per kg. So this cancel. That is you will get in kilo divided by 15.2 divided by 15.2, right? So that is nothing but equal to 21.98 megajoule. 21.98 megajoule. And this is nothing but equal to 6.108 kilowatt hour. See here, kilowatt hour, right? So try to observe the conversion. So here, how that take the calculator and try to see it whether you will divide or you will multiply uh, by 3600, right? So that is how you try to work it out. But the answer is 6.108 kilowatt hour, right? See, the thermodynamics, how it is connected in a real situation. That is what in the overview of the thermodynamics course, what I told you that all the natural processes occurring in the nature are governed by the thermodynamic laws, whether it is zeroth law, or, first law, or second law. So try to recapture that particular points what I discussed earlier. Next, so the two Carnot heat engines A and B, and these are in series. These are in series. That observe this particular parameter because it comes under to the absolute scale of a temperature. So two Carnot engines A and B are connected in series. Connected in series. So here two Carnot A and B are connected in series between two thermal reservoirs 1000K and 100K respectively. Engine A receives 1680 kilojoules of heat from the high temperature reservoir and rejects heat to the Carnot engine B. Engine B takes in heat rejected by the engine A and rejects heat to the low temperature reservoir. If engines A and B have equal thermal efficiencies, then determine the heat rejected by this particular side. So drawing the diagrammatic sketch for this particular, so this is the engine A and the engine A is connected like this portion, that is here. Heat engine, Carnot heat engine, that means Q1, Q2, and it is operating in between the 1000K. Next one is the from this one, that is it is utilized by the engine B, taking this particular heat, that is Q2, and rejecting the heat. This is nothing but 1000, sorry, it is 100 Kelvin only. So this is Q3, that is Q3, right? So here also you will get the work output from the A, and here also you will get the work B. So these the engines are connected in series. Engines are connected in series. See, there could be the two engines, or three engines, or four engines, or 10 engines, or 100 engines in between the source and sink, right? So then whatever it may be the engines, what about the heat absorption and what about the heat rejection? So that particular things have to be observed. So in this particular case, what are the things is given? So first thing is the efficiency of A is equal to the efficiency of a B, because the efficiencies for this engine A and engine B is mentioned, right? So we don't know the temperature, intermediate temperature we don't know. We don't know the intermediate temperature, right? So this is nothing but the intermediate temperature. So like this, the intermediate temperatures, if there are 3 to 4 engines are there, you can get the 2 to 3 intermediate engines. So this I don't know. So for this particular case, I need to find out the intermediate temperature T divided by 1000. And for this engine B, 1 minus T, sorry, this is 100 because the low temperature is 100. This is 100. The low temperature is 100 divided by T. So from this case, you can get the intermediate temperature value as T is equal to, that is the root of T1 and T2, that is 1000 into 100. You will get that value as 316.3 Kelvin, right? So in the same way, you try to get the Q2 value, right? So that is the Q1 by Q2 is equal to T1 by T, because this Q2 is connected to the T, right? Or you can also go for the, here, if you want, you can use this particular T2 and T2, this is T2, right? So that is the heat separate, this is the T3, right? So you can get that is T intermediate temperature is equal to